In this program, we're going to visit the post office. Now, the post office is interested in letters, and we're interested in mathematics. So, what's the connection? Well, in this program, we're going to explore a branch of mathematics called group theory, which will help us solve and understand some of the problems involved in handling mail. Mail collected from pillar boxes comes into the sorting office as a mixture of letters and packets of all shapes and sizes. Segregating the letters is done in machinery, which also shapes the letters onto their longer sides and removes the oversized items. By the time they leave this machine, the letters have been stacked in piles of similar size, arranged with long edges parallel. Not all the stamps, however, are in the upper right-hand corner. The machine that this man is feeding is the one we're interested in, the automatic letter-facing machine, or ALF for short. Its function is to face the letters, that is, to arrange each letter so that its stamp is on the upper right-hand corner, and incidentally it franks them and sorts them into first and second class. The question is, how does ALF do it? Well, let's try to understand the problem. In order for the letter to be franked, and when it left your hand, it should be in this position. Now, in its passage through the pillar box and through the office, it probably can end up in any one of these 4 different positions. Now, this branch of mathematics called group theory is going to help us design a machine which will enable us to face letters. And Don is going to show us how that's done.
Before worrying too much about how to design a machine to do this, let's have a closer look at the position. The fact is that corresponding to each of the 4 positions in which the letter can arrive, provided it's standing on a longer edge, we can define precisely one action which will face it. For instance, in the unlikely event of it arriving the right way up, as here, then the action I require is very plain, no action at all, no action. If it arrives like this, then all I have to do is rotate it. I rotate it either way, doesn't matter, to 180 degrees. Third possibility, back of envelope towards us when it arrives, flap at the top so the stamp's really behind here. I have to turn it over. Now, in order to turn it over, there are 2 possible ways I can turn it. And in this case, I have to turn it over or flip it about a vertical axis. So. And lastly, again, back towards us, flap at the bottom, stamp, in fact, here behind. Again, a flip. This time, a flip about a horizontal axis. So there we are, 4 actions defined, each of which puts a wrong position right, except the first one, which does nothing. Now, we have flip H, flip V, rotation R, and no action. If we could just have 4 stamp sensors, one in each corner of the letter, This might be a bit difficult to arrange. We'd have to shuffle them around so that they fitted each letter and letters of different sizes. It would immediately identify which of the 4 positions the letter was in, and it could then automatically perform the one correct action. Now that would be uneconomic, to say the least, because partly of the sliding about and partly of the 4 sensors. Perhaps more sensible would be to try and arrange to have just one sensor in a fixed position and push all the letters up to it, say so at the top right-hand corner of the letter met the sensor. The sensor would then tell us, is the stamp there or isn't it? And from then on, we might be able to devise a better procedure.
Well, I think we just might be able to manage that, Don. And here's a possible block diagram for such a machine. How does it work? Well, supposing a letter comes in here the right way, then the sensor sees it's the right way, so it shoots it straight off here to be franked. Now, supposing a letter comes in like this, the sensor says, well, that's no good, does a horizontal flip to it, detects it's right, and sends it off to the right to be franked. What about a letter coming in like this? That's no good. Machine does a horizontal flip. Unfortunately, that's still no good. So it undoes it, that's just H again, and now applies a V to it. It sees that V is good, and so it sends it off to the right. And so on. I needn't go into all the gory details, but you can see that by this process I can also get an R, and so I can get all the 4 possibilities for writing a letter. Well, that's a very nice sort of a machine, but it's a bit naive. So let's call that Mark 1. Why is it naive? Well, at this point, when a letter came in, I un-H'd it and then V'd it before sensing again. That seems a bit silly. Could I not possibly combine the H action and the V action into one single action and save time? Well, let's see how that might be done. So let's see what the problem is. The problem is I've got a letter which has been righted by having an H and a V done to it, and I'd like to know what was the original position so that I can see what single action would have done that. Seems a bit tricky, but I can solve this problem by working backwards. Remember, what's happened is that the letter has been V'd. That means the intermediate position was like that. Then afterwards, the letter has been H'd, and so the starting position must have been like that. So I've solved the problem. This, in fact, was the starting position, and so by a R action, I've managed to get the letter into the right position. So I can combine the H and the V action by using a single R action. Well, that's very satisfactory. Now, perhaps we can use other combinations of actions to economize our machine. And examining this problem is our first great leap into group theory. And Don's going to have a look at that for us now.
Well, here's a table on which I'm going to record all the possible combinations. And Alan's told us one already. He says that H and then V is R. And here's my R. Now, it has to go in the table somewhere, but where? Well, it's H, then V. The first action is H, so it'll have to be in the H column. The next action is V, so it's in the V row. That's where it's got to go. Well, that's straightforward enough. Let's do another. What about V, then R? Here's a letter, the right way up. I'm going to V it and then R it. First of all, the V, that's a flip about the vertical axis, and now a rotation. Now what have I done to it? I have, in fact, you can see where the stamp is, it's this side, so I have, in fact, H'd it, look. So V, then R, is the same as H. Well, what about, say, H, then H? Here we go. H, and H again. It's no action. Now, I don't have a symbol for no action. Actually, I do, of course. It's conventional to represent the no action by a capital I or a lowercase letter e. I'm using capital letters here, so I'll use an I. You might remember the I for the identity matrix in multiplication. Here's my I, H then H is I, the identity, the thing, the action which leaves the object identically the same as it was before. But now my table's gone wrong. I've got I's in here, but no I's in the headings. So it won't do. I shall have to add I's to both lots of headings. I column head, I row head. Now it's easy to see what the entries in the I column and the I row are going to be. They'll have to be the same as the headings. There's no need to do all the rest of it. Let's magic it in. So now we have a complete closed table showing the result of combining any two actions. And perhaps Alan can use this to improve the design of our machine.
Well, I can certainly use Don's table. You see, in our original mock-up, we have the actions H and V, and from Don's table, and we already saw this previously, H and V is R. And so I can replace these two actions by the single action R. Further down the machine, I have V and R combined. Now, what do they give me? Well, V and R gives me H, and so I can combine these two actions by the single action H. And this Mark II version is a much improved machine. First of all, it uses fewer components, and in fact, it only uses two sorts of actions, H and R. And you can probably do better. Suppose an engineer tells you, well, R's a bit difficult. Why don't you design a machine using H and V? Is that possible? Well, by using the group table, in fact, it is possible. And what's very funny is this is the way the post office does it. The letters, neatly stacked, but with stamps any old how, are carried on a continuous belt round the machine to the stackers at the end. On their way, the stamps are detected by a sensor, but they don't change their orientation relative to the belt until they come to this twist, seen here in slow motion. The diverter splits the letters into two streams, those to be H'd and those not. The bottom belt gives its letters an H twist, the top belt edge onto the camera, and above the return belt bypasses this H and returns the letters straight to the main stream. This process isn't completed yet because the letters have to be scanned, and then there's the decision to V or not to V. Well, we've seen this complicated machine perform the H process, but how does it V it then? Well, in fact, this is how it's done. Well, that's like the end of our letter-facing story, and it's certainly the end of the first part of the program. But what have we done so far? Well, we've obtained a table which summarizes for us the effects of combining actions on letters. And if that's all there was to it, it would be pretty trivial. But in fact, there's much more to it than this. You see, this is our first example of this famous mathematical structure we were going to tell you about called a group. Now, what is a group? A group is a set of elements with a rule for combining the elements. Now, the rule has certain additional properties which are very important. But before we go on to list these properties, let's give you another example of a group.
Our letter-facing group, which incidentally is usually called the rectangle group, consists of the transformations of a rectangle which leave it fitting in the same basic position. Now, technically, that's a symmetry. Now, we need another group, and I'm going to use an equilateral triangle. Now, an equilateral triangle has more symmetry, in a sense, than a rectangle. There are, in fact, going to be 6. And I'm just going to define 6 different transformations. Here, plainly, is the first one. rotate it to 120 degrees anti-clockwise. There it is. I'm going to call that R1. Next, of course, I can rotate it through 240 degrees anti-clockwise, or if you prefer, 120 degrees clockwise. 1, 2. And I'm going to call that R2. And lastly, for the rotations, I can turn it completely around, which will obviously achieve nothing at all, and I'm going to call that, obviously, I for the identity transformation. Now the flips. First, notice that the flips are defined in terms of the letters of the frame, A, B, C, irrespective of where the letters of the triangle are. Flip A is a flip about an axis through the A of the frame. So, even if the triangle were in a different position to start with, flip A would still be this flip about a vertical axis. So flip A, starting from that position, is that. Flip B, fairly obviously, is a flip about the B of the frame. Called FB. And lastly, flip C, flip about C of the frame. And that's the lot. Let's just put the names on. And now let's get on with combining them. 2 points, small points, both conventional. You've noticed that we've missed off the words first action, next action. They're just not normally there. You're expected to remember in a symmetry group table that this is the first, this is the next. The other point, much more useful convention really, is that one begins the headings with I in both cases. You'll see the value of that later. Right, well the I row and the I column aren't exactly interesting, so I won't bother with them. The R1 row, well, we've done that one effectively. What goes in there? It's R1, then R1. So let's do it. R1, and then R1 again. There we are. What's that? I reckon it's R2. Next one, R2 first, then R1. Reinstate this, go back to the same position. R2 first, and then R1. Hardly needed doing, did it? I. Next one, flip about A first, and then R1. Flip about A first. Now R1. What's that? That, I think, is flip about C. Now, I've been making something of a fuss about first action and next action, although we've missed them off. And the fact is that if you take the same two transformations and combine them in a different order, it's entirely possible you may get a different result. In such a case, the operation, of course, is non-commutative, and we have an instance here. This is flip about A followed by R1, and we get FC. I'm now going to do the same two in the other order. That is R1 followed by flip about A. R1, now flip about A. That is flip about the vertex of the frame marked A, which is up here. It's got nothing to do with this. Here we go. And that, well, what is it? I think it's flip B. Two different transformations. Well, I'm not going to do any more. You can fill it in for yourself afterwards. Now let's get on with trying to derive the properties of a group. Alan.
Well, here are the two groups whose group tables we built up during the program and from which I want to extract the properties. In fact, there are 4 properties, but before I even look at that, there's one basic property which comes before that, because this tells us that, in both cases, a group is a set of elements with some rule of combination between them. Now, what are the 4 properties that this rule of combination has? Well, first of all, we had closure that Don was talking about. If x and y are elements of the group, then x combined with y, and I'm using star for the combination, is also a group element. The next property was the fact that there's that very important element called the identity element in both groups. And the next basic property is that of having an inverse. Remember, in the triangle group, the element R1 combined with R2 to give the identity. So I could say that R2 undoes the action of R1. So for every element x in a group, I have an element x tilde, which undoes the action of x. That is, x combines with x tilde to give them the identity, and the other way. Now, the last property, it's a bit technical. It's called the associativity property. It arises like this. Remember, our group table tells us how to combine 2 elements. Now, what happens if I want to combine 3 elements? Is it x combined with y and then the result combined with z? Or do I have to do it this other way? Well, my associativity rule tells me they're equal. Now, I really want to change my point of view at this point in a very, very interesting way. I mean, these are properties of those groups. But what I want to do now is say that these are, in fact, the axioms of a group. Now, what do I mean by axioms? I mean that we're going to set down these rules, and we're going to claim that any mathematical structure which consists of a set of elements and rules for combining them will be a group if the combination rule obeys these properties. And it doesn't matter where you got that structure from. It'll be a group. For example, if I take positive real numbers under multiplication, can I check these 4 axioms now? Well, if I multiply 2 together, then I get another positive real number, so it's closed, closure holds. What's the identity for multiplication? Well, the number 1, of course. For every positive real number, do I have an inverse for multiplication? For example, for the number 2, the inverse would be the number 1/2. That's easy enough. And numbers under multiplication are associative, so that holds as well. So positive real numbers under multiplication give me an example of a group. Actually, it's a rather fascinating group because you couldn't write down a group table in that case. What about real numbers themselves under multiplication? Well, that would fail to be a group because the axioms don't hold. Which axiom doesn't hold? Well, the inverse one, because the number 0 does not have an inverse for multiplication. Well, these are just a couple of examples. If you want to see some more examples, you'll find them in the correspondence text and in the tape associated with this program. But all of mathematics is just littered with very important examples of groups.